So in today's lecture in Lie algebra, it is lecture 30, chapter 6, which is solvable Lie algebra, and I will be doing some exercise problems on this. So let me start with the class. Okay, so exercise 1, okay, first one, okay, it is, suppose phi of, suppose phi of L1 tending to L2 is a surjective homomorphism. Okay, this homomorphism is of whose homomorphism it is? Of Lie algebra homomorphism we are talking about, okay? And I have to show that phi of L1 of k in the bracket k, okay, is equal to L2 of in the bracket k is there for all k belongs to natural. Now this is proved by induction. I am going to prove this by induction, okay, mathematical induction. So let me start with it. So for what you'll have to do now is put k is equal to 0. Now phi of L1 of 0. Now how you all got this? So wherever there is k, you all have to replace it by 0 now, okay? Because for k is equal to 0 it is. So that's what I have done. Phi of L1 of 0, which is equal to phi of L1. Now this is nothing but L2. Why? Now this is equal to L2 of 0, which is nothing but L2 over here, right? See over here, L2 of k, where I am replacing it by 0, which is nothing but L2. Now you all have to assume that phi of L1 of raised to power of n is equal to L2 raised to power of n, okay? Next, what I have to show that is phi of L1 raised to power of n plus 1 is equal to L2 raised to power of n plus 1. I have assumed this and I have to show this to show that this. Now I take this one, phi of L1 raised to power of n plus 1 in the bracket and this bracket, okay? So take this here. Now this is equal to what? Now this is phi of L1 raised to power of n plus 1 is equal to phi. Now this is written in this form. Phi of L1 raised to power of n, Lie bracket of this, comma this. L1 of, sorry, not phi of bracket L1 raised to power of n, comma L1 raised to power of n, okay? Now this is equal to what? Now this phi you will have to place it inside. So phi of L1 raised to power of n, comma phi of L1 raised to power of n. Now this is equal to what? L2 raised to power of n and L2 raised to power of n. Now how I got this? You all have understood this step, right? Now how to do this step, how I got this step also you all have understood. Now how you all got this? Wait, let me tell you all. Can you see this? When I was told you all to assume that phi of L1 raised to power of n is equal to L2 raised to power of n. So that's what? Phi of L1 raised to power of n is nothing but what it is? L2 raised to power of n. So that's why I have put L2 raised to power of n, comma L2 raised to power of n, okay? And now this is equal to what? Lie bracket of L2 raised to power of n, comma L2 raised to power of n is nothing but L2 raised to power of n plus 1 in the bracket, okay? And so we are done with this problem, with this exercise problem. Next, let me do the other one, okay? Other exercise problem. That is, if M is a subalgebra, of L, then show that M raised to power of n, this is a subset of L raised to power of n, okay? And this is proved by induction. So if I put n is equal to 0, what you are going to get is M of 0 is equal to M, which is a subset of L, and this is nothing but equal to L of 0. And this implies what? Have you understood this part? Wherever there is n, you all have to replace it by 0, and this is nothing but m, which is a subset of L, which is nothing but equal to what? L of 0. Why it is L of 0? Because what is L of 0 is nothing but L, right? And this subset is because of this. And now this implies what? M of 0 is a subset of L of 0. Now this is a subset of this, okay? Next is, you all have assumed that M of k is a subset of L of k, okay? Now to show that m of k plus 1 raised to power of k plus 1 is a subset. Yeah, so this was a subset of this. I have said L raised to power of k plus 1. Now take this one, m raised to power of k plus 1. Take this, which is equal to Lie bracket of m of k comma m of k. Okay, and this is a subset of, we write in terms of subset because of this. Wait on. Yeah, because of this. So this is a subset of what? What is m of k is a subset of L of k, right? So that's what. Wherever there is m of k, I have written L of k. Why? Because of this step. Okay, comma L of k. Now this is equal to what? This is nothing but equal to L raised to power of k plus 1. And I have already taught in your this chapter, okay, in this chapter of this chapter, I have taught you all that what is the approach 1, approach 2. How you all have to go through it. Please do that so that it will be helpful for you all to understand these lectures now. Okay. Now this implies what? M of k plus raised to power of k plus 1. Now this is a subset of this L raised to power of k plus 1. Okay. Have you understood this step? So okay. Now what I'll have to do is hence m raised to power of n is a subset of L raised to power of n for all n belonging to natural by principle of mathematical induction. This is your final statement which you will have to say. Next, one more let me do. Exercise 3, okay. What I will be doing is L raised to power of m. Let me write the question, okay. This raised to power of n is equal to L raised to power of m plus n for all m comma n belonging to natural, okay. Now this is proof by induction. Proof by induction. For any fixed m belonging to natural, m is arbitrary, okay. So put let n is equal to 1. This actually I want you all to try it, but I am solving it over here for you all, okay. L raised to power of m into this raised to power of 1 is equal to, this is nothing but L raised to power of m dash, okay, and this is equal to nothing but L raised to power of m comma L raised to power of m, and this is equal to, okay, sorry, it's not like this. Now this is equal to, how we write this as L raised to power of m plus 1, right? And in the previous lecture, meaning previous thing, I have done some mistake, I guess. Yeah, right. Just do some correction over here. Put the bracket over here, okay? Now let me. So yeah, L raised to power of m plus 1. Now you all have to assume that L raised to power of m, outside put the k, is equal to L raised to power of m plus k, okay. This is m plus k. Write it properly, okay. M plus k. So L raised to power of m into okay, raised to power of k is equal to, put it is equal to sign properly, okay. This. Next, let me do. Okay, so after this step, I move to this step, okay. Now to show that L raised to power of m into meaning raised to power of k plus 1, just put that bracket over here properly, okay. Now is equal to L raised to power of, in the bracket write down m plus k plus 1, okay. Now this is what, now take this part here as it is, L raised to power of m raised to power of k plus 1 is equal to, now this is written in this form, okay, L raised to power of m plus k plus 1, okay. And now further what I will be doing is write this part as it is again over here. Let me do this. L raised to power of m into raised to power of k plus 1 is equal to, in the bracket, and again the bracket, L raised to power of m raised to power of k, and this is raised to power of 1, and this is equal to what? I write it, so I have written it on this page. Now this is equal to L raised to power of m plus k in the bracket, which is raised to power of 1, okay. Now this is written as leave bracket of L raised to power of m plus k comma L raised to power of m plus k, and this is as usual. Now this is equal to L raised to power of m plus k plus 1, okay. Basically okay, I'll explain you all on the next, okay, here only somewhere. Suppose if it would be L raised to power of it, not here, some other color. This is roughly explanation will. Suppose something was L raised to power of m comma L raised to power of m. How we write this as L raised to power of m plus 1, right? If it would be L raised to power of k comma L raised to power of k, it would be L raised to power of k plus 1, something like this, right? Just a roughly explanation, okay? Because before that also we have done the similar problems. Yeah, here. Now this leave bracket, I was writing it as what? K plus 1, okay? So with this I'm done with my today's lecture, and in the next lecture I will be proving more exercise problems and proofs. And thanks for watching.